Hello everyone. For this tutorial video, I'd like to explain how to derive the volume and surface area of a sphere, which unfortunately do not follow the simple tricks of cylinders or cones, owing to the fact the cross-sectional area is constantly changing, unlike a cylinder, and the fact the endpoints of the sphere are neither flat circles nor tips, but rather bumps that are curved in both directions, i.e. the left and right and the up and down, as opposed to the more simpler curves of the cylinder or cone, which are only curved in the left and right direction. If we were to extend the Pythagorean theorem into 3 dimensions, we would see that not only is r squared x squared plus y squared what we already know for a circle, where x and y are the horizontal distance and the vertical distance from the center, but it can also be shown that a 3D radius, which we will denote capital R, can be seen with the diagonal of another right triangle, where the first leg would be the 2D radius, and the second leg would be z, or the height from the origin. So in conclusion, capital R squared equals lowercase r squared plus z squared. And since we know already lowercase r squared equals x squared plus y squared, we plug this in and get capital R for 3D radius squared equals x squared plus y squared plus z squared. And so we use this formula to denote the radius of a sphere and explain that a sphere has a constant 3D radius, just like a circle has a constant 2D radius, meaning all of its points are equally distant to the center, which is neither true for cylinders nor cones. Although it is convenient to know the definition of a sphere, this will not help us find anything regarding the surface area or volume, so we would have to use an entirely different method. With some creative thinking, we can see that we can put a cylinder whose radius is equal to its height and a cone whose radius is equal to its height all together, and subtract parts of this overall volume to get a spherical result. If we were to arrange these in a way that they would line up, we would know their cross-sectional areas line up too. And we know the cross-sectional area of a cylinder is pi r squared, and the cross-sectional area of a cone is pi c squared, where c is the cross-sectional area at a particular point, as we must keep in mind that it varies constantly. And so does the cross-sectional area of the half sphere these would make up. If we were to simplify our examination into 2 dimensions, so that we do not get bogged down in unnecessary details, we would see that the cone becomes an isosceles triangle, and that the height of the triangle would match the radius of the half circle. And we can also next make a triangle that was not part of the original cone, whose leg opposite the right angle is equal to the radius of the semicircle, and whose length is similar to the radius of the semicircle, and whose height is equal to the radius of the semicircle. With this breakdown out of the way, we can see that the cross-sectional area of the cylinder plus the cross-sectional area of the hemisphere must be equal to pi times height squared of similar right triangle plus pi times the radius of the semicircle squared minus the height of the similar triangle squared. And this simplifies to, once we multiply pi across the second term, pi times radius of semicircle squared, as the other 2 terms cancel each other out. So it should be seen that the volume of the cylinder minus the volume of the cone is exactly equal to the volume of the hemisphere, which, since it is pi r cubed minus 1/3 pi r cubed, simplifies to 3/3 pi r cubed minus 1/3 pi r cubed to 2/3 pi r cubed. And if we know by definition a hemisphere is half a sphere, it should follow that 2/3 pi r cubed times 2 is 4/3 pi r cubed. Since we have explicitly demonstrated that a hemisphere is a cylinder minus a cone that have matching radiuses and heights, we should see the surface area would be the surface area of a cylinder minus a cone with equal radiuses and heights as well, which, since the radiuses of the bases match, cancel each other out, would be 2 pi r times height, the surface area of the part of the cylinder that is not the bases, minus the sector of the circle that constitutes the height of the cone, and plus pi r squared for the topmost base of the cylinder, as the cylinder has two bases while the cone does not. And we remember that in the case of a sphere, the height is equal to the radius. It should come as no surprise that the formula involves an r squared factor, and the exact formula would be 2 pi r squared plus pi r squared of the topmost face. So the surface area of a full sphere would be 4 pi r squared, but without that extra factor, as we no longer have any surfaces that can be described with perfect circles. Join me in the next tutorial video where I explore how to figure out sectors of spheres, which technically we already figured out with the hemisphere, but I can show you a more explicit formula that works for any sector of a sphere and not simply half.